Okay, so the next presentation is from Domingo Santos Rodriguez, who is a senior researcher at TECNALIA. Min, can you change the slide?
Yes. I think, yeah, wait a moment.
Oh, no, yeah, okay, great.
Yeah, I have to try it now, yeah.
Yeah, now I can see you. So a couple of words about you. So you have really more than 4 years renewable energy experience covering most of the value chain of the photovoltaic technology. Joe's topic is detection and diagnosis of failure modes based on the array state parameters, PV metrics, and ML approach. And he's basically contributing towards a GoPV project. Jos, I'm sorry if I mispronounce your name, but you know, please.
It's okay.
Please start your presentation.
Thank you. Okay, so yes, my name is Jose Santos. I work in TECNALIA as a senior researcher, and I'm going to present you detection and diagnosis of failure modes based on the array state parameters, PV metrics, a machine learning approach, and with my colleague Giosue of the RSE. As you probably know, the LCOE of new PV plants is calculated with an expected lifetime of around 30 years. This means that continuous operation and maintenance tasks are required to maintain the energy production level. And nowadays, the operation and maintenance is usually based on the schedule of on-field task, which is inefficient and costly. So let's say that the predictive operation and maintenance solve these problems by means of a remote analysis of the SCADA data that determines the optimum time for the on-field tasks. So our main objectives is the development of a software tool that takes the input SCADA data and provide us with a list of possible failure modes. Two different approaches have been followed. The TECNALIA approach is based on the array state parameters, and the RSE approach is based on PV metrics and machine learning. Specifically, the TECNALIA approach is a hybrid physical statistical. On one hand, it takes advantage of pre-existing models used in photovoltaics that allows to the detection of failures even with short data series. On the other hand, it uses different data-driven techniques to improve the reliability of the results and the sensitivity of the failure detection. Our failure detection and diagnosis tool can be divided in 4 steps. I'm going to present you some examples of results that we have obtained from real SCADA data, but also from synthetic data with simulated failure modes. The first step is focused on the data processing. I'm going to present you a couple of examples. One of the algorithms is devoted to the detection of clear sky moments, which use external data from satellite database. The labeling of these clear sky moments can be used to reduce the results uncertainty. A second processing algorithm is devoted to check the linearity of the correlation between the maximum power point current and the irradiance measured in the plane of the array. The preliminary results of the SCADA data show that misalignment between the sensor and the plane of the array is something common, which produce this, let's say, elliptical shape So our algorithm carry out a correction of the measured irradiance based on the level of misalignment. The next step is the failure detection of our failure detection tool is the calculation of the array state parameters, which provide us with information about the state of health of our PV array. I'm going to present you a couple of examples. One specific algorithm is devoted to the identification of the time when the maximum power point correspond to open circuit voltage. From the later analysis of the open circuit voltage data at different irradiance and temperature, a set of equations is obtained which can be used to produce the VOC. Additionally, a set of array state parameters are also extracted, among them the VOC at the standard test conditions. In this example, it can be observed how two PV arrays of different PV module technologies present differences in the degradation level of VOC, which could be linked to a specific set of failure modes. I put you here some examples. A second algorithm is devoted to the analysis of the temperature coefficient of the maximum power point voltage. The obtained results suggest that this temperature coefficient depends not only on the wind speed, but also on the location of the array in the PV plant. So this information could a priori be used to determine which parts of the PV plant are hotter, an information of interest, considering that these regions are more susceptible to failure. The combined information of the open circuit voltage and the maximum power point voltage makes also possible to carry out an estimation of the series resistance of the PV array. Specifically, a series resistance greater than that obtained from the PV module characteristics is obtained. Although this is compatible with the existence of extra coupling resistance, please notice that the increase is much higher for one PV module technology than for the other. This could be a consequence of different types of or specific type of failure modes. The next step is devoted to the failure detection and diagnosis from the array state parameters. On one hand, we have defined a set of equations for the normal operation of the PV plant, and we can use this set of equations to detect possible deviation due to the existence of failure modes. On the other hand, we have a set of multiple array parameters that could be affected or not depending on the failure modes. In fact, our tool tried to do a diagnosis of these failure modes by means of what we call as an array state parameters footprint. So basically, we define a array state parameters footprint for each type of failure mode. The last step is focused on the calculation of the energy loss once a failure mode has been detected. Basically, we are going to use our set of normality equation to forecast which is the energy production after the array state parameters have been modified. We have checked the reliability of this procedure by using a synthetic dataset simulating different failure modes with a standard diode model. Here you can see the comparison. The obtained results show a relative error of our approach, our ISP approach, of less than 1% for the energy production, and an error of less than relative error of less than 5% for the energy loss forecast. An additional advantage of our approach is that some array state parameters can be directly correlated to specific type of energy loss. And this allows us to carry out a disaggregated analysis of the energy loss. In other words, we can assess the contribution of each failure mode to the total energy loss. With this information, we can calculate the cumulated energy loss for each failure mode. So by means of an euros per megawatt hour factor, the associated revenue loss can be calculated for each failure mode. And this information, combined with the cost of identification and repairing of each failure mode, give us the possibility of optimizing the time when the corrective action should be carried out. I would also like to thank to the rest of the team of the TECNALIA group that is working in this and the development of this algorithm. Basically, that is all from my side. And now it's your turn, Josue. Sorry. Yeah.
Okay, can you hear me?
Yes.
Okay.
Yes.
So Sharma, I'll continue the presentation, or you introduce?
Yes. So he said he will directly take it up because it interrupts the flow.
Okay, so I continue. So I guess you can see the presentation as well.
Yes.
Yeah. So thank you also, José, for the introduction to this second part of the presentation. So in my presentation, I'm going to talk about fault detection diagnosis algorithms that are based on three main algorithms that has been developed having three different scopes. The performance ratio metric algorithm is to have information about the PV system performance, fault, and health. Multiple regression models have the scope to extract information by inverter main parameters. And the clustering approach is to have information about fault that previously were not characterized due to, for example, new failures modes, new components, and new technology in the PV system. So here I show you the scheme of the fault detection and diagnosis approach and the pipeline that follows. So after that, SCADA collects data in a specific precondition for the specific fault detection diagnosis algorithm. Here, the three approaches that has been developed by RSE. We talk about performance ratio algorithm to monitor the PV performance and detect anomalies at system level. Of course, PV field technicians are then supported by this algorithm, having a reliable interpretation of this performance metric. Then a multiple regression model to monitor the main inverter parameters to HighLite malfunction at inverter level. And the clustering approach that, let's say, based on the analysis of the specific PV plant we are monitor, it is able to detect faulty conditions that previously were not labeled by the PV operator that can arise in PV system consisting of new PV components. Let's say it has some advantage that we will see later in details. So regarding the performance ratio, instantaneous performance ratio is calculated, can be distorted by, for example, dirty or not calibrated PV reference cells, or variable sky condition, or from the environment, or low values of irradiance may lead to unstable PR. So if instantaneous performance ratio values are labeled, taking into account all these conditions, of course, it can provide useful information about the PV system health to the PV operator. So the proposed algorithm identified the status of the PV plant by applying a set of thresholds to each performance ratio measurement, which is computed every 5 minutes. So an alarm is triggered only when an issue is observed for more than 30 minutes consecutively. But all conditions about unstable irradiance or unstable PR due to, for example, MPPT tracking errors are taken into account, in this case, avoiding superfluous interventions by the technician. So in green, you can see here an unstable condition that in general do not activate any specific system alarm, but give an indication, a warning, let's say, while in red, there is an alarm that is activated due to a a system fault or a PV string fault. So automatically allow to the technician to be advised about the specific faulty condition. Okay, then we move to the second part, the multiple regression models that has been developed considering and monitoring the main PV inverter parameter. So monitoring the main PV inverter parameter, for example, inverter temperature or supervisory board temperature internally of the inverter, it is possible to detect, for example, fault at inverter level. So in this case, a specific regression model has been developed for inverter board temperature and output power of the inverter. And then a residual analysis or deviation between the measured parameter and the expected parameter by the model allow to check malfunction at inverter level, for example, in this case, a condition of over temperature of the inverter. Last fault detection and diagnosis algorithm is based on a clustering analysis, which is an unsupervised method. Why it is important? Let's say it's like if we see the PV system or the PV string, the PV array, the piece of PV system that we are analyzing, like a black box. And in this way, the clustering algorithm is used to detect data which have pattern of fault. So here you can see the list of variables in this case that we use to the cluster analysis. A normal operation condition is clustered here in blue, while all the other clusters represent system fault or SCADA communication error that has been taken into account also because SCADA communication error need to be managed also by the PV operator. Which is the advantage of this approach? The advantage is that it can detect fault and continuously learn about new possible faults that previously were not labeled. For example, due to new components or new failure modes, new PV technologies. So once discovered, like in this case, each cluster is characterized. The new pattern of fault can be then classified, like in this case, to a later recognition. So it's classified and labeled by the system to a later recognition. So in conclusion, we've seen this presentation for both TECNALIA and RSE, the different fault detection and diagnosis approach that have been proposed by TECNALIA and RSE, which are the conclusion. The array state parameter approach allows the failure detection from short data series while improving sensitivity. Clear high detection of plane of array misalignment correction are used to improve reliability of result. the array state parameters like, for example, open cyclic voltage, temperature coefficient, series resistance are used to determine the health state of PV array. The array state parameter footprint allows the identification of a wide array of failure modes. Normal operation models that defined by the array state parameter allow a forecast of the energy loss. Disaggregated analysis of energy loss can improve the decision making of the operation and maintenance task. Regarding the RC conclusion, of course, the PR metric-based algorithm allow to trigger, activate different alarms which correspond to different severity level. And it can support automatically the PV operator or when it's recommended the intervention of the technician. While the multiple regression model on the inverter, the main inverter parameter, allow to have a better understanding about the full alarm at inverter level to the diagnostic of the type of fault, while the clustering algorithm allow to detect faulty conditions that previously were not labeled by the PV operator that can arise or can be detected in PV system consisting of new components, new technologies, or new failure modes that previously were not characterized. Which are the next step of this development in RSE, in RSE and TECNALIA, in the GoPV project? GoPV fault detection diagnosis will then be validated in an integrated pilot in southern Italy, in energy power sites in Passo Martino, Catania, where a specific PV array will be devoted to introduce a specific failure mode in the PV system. So all data collected from this PV array will be then analyzed and processed to the fault detection diagnosis algorithm. This is all. I want to thank you, all of you, for the attention.
Okay, thank you very much for a very nice talk. And sorry, I think I messed up. I could not introduce you. But I think you both really managed to do it on time. So thank you very much again for your contribution. And I think there would be some questions in the chat window. It would be great if you can answer these questions. I think I already see there is a question for you. Could you please answer in the chat window so that we can move to the next presentation?